All right, here we are with the Sn1 mechanism. S for substitution, N for nucleophilic 1 because it's unimolecular. Follows first order kinetics. It's a first order reaction. So if we had this reactant right here, tert-butyl bromide, and again with our acetate, we are going to just substitute this oxygen for where the bromine is, and so the bromine's not here anymore on this carbon, and the oxygen is now on there of the acetate. Note, as we've said before, when a nucleophile attacks, the nucleophile stays together. No bonds break when a nucleophile attacks. It all stays together. Now, yes, there might be a deprotonation reaction that'll happen later, but during the nucleophilic attack stage, the nucleophile does not break up at all. Note, this is a Sn1 unimolecular. The rate law is rate equals K times the concentration of the substrate, concentration of the alkyl halide. The concentration of the nucleophile is not involved. Okay. This is a two-step mechanism. The first step is a slow step. The first thing is the leaving group just leaves. This is a situation we were looking at before where we have our alkyl halide. We've got a nucleophile over here, but the first thing that happens is just this. Nucleophile leaves, or excuse me, leaving group leaves. It just leaves, leaving this thing by itself. And then a little time later, then the nucleophile comes in to attack that carbon. And the nature of this beast, this carbon that has 3 bonds coming from it, after the leaving group left and took its electrons, 3 bonds and no lone pairs, that's what's going to determine, that's what is going to give us all of the properties of this mechanism. Because it gives us a carbon with a positive charge, a carbocation. Now, the first step is a slow step. The leaving group just has to leave to give us this carbocation. Then, once we have the carbocation, we've got a positively charged carbon. That's unstable. Now the nucleophile will come in and attack that carbon to give us our product. So it's a two-step mechanism. Slow first step to generate the carbocation. Fast second step, nucleophile attacks a carbocation intermediate. If we did potential energy versus reaction progress, this is the deal here, where we go up the hill to break that bromine off, and then we're at our intermediate carbocation. Note, carbocations are higher in energy than your starting material. Carbocations are unstable compared to your alkyl halides. Then a very low hump, which means a very fast reaction of the nucleophile coming in and attacking that carbocation to give us the product. All right, you say, well, that's all nice and dandy, but what about the stereochemistry of this reaction? Well, I'm glad you asked. Carbocations are trigonal planar, which means once this leaving group leaves here, we've generated a carbocation because it took both electrons. We've got a positive charge on this carbon right here. It's a carbocation. It is trigonal planar. It's a trigonal planar molecule. So the question is, what side can the nucleophile come in on? Well, it could come in from the right side, or it could come in from the left side. Note, if the nucleophile comes in on the right side of this carbon, it's going to shift all 3 of these groups. They're going to flop towards the right to give this molecule here. If the nucleophile comes in from the opposite side, the left side, it's going to shift all these guys. They're going to flop to the left to give this guy. What's the relationship between this product and this product? They are non-superimposable mirror images of each other. These are the 2 enantiomers. What's the chance that the nucleophile comes in on this side compared to this side? It's a 50-50 chance. So what that means is when you do an Sn1 reaction with a carbocation that is chiral, if the product's going to be chiral due to that carbocation, you will get a racemic mixture of the products. Okay. Now, what reactions happen faster? It turns out that methyl and primary alkyl halides are very slow with this reaction. Primaries, they're okay. They're a little slow. They're not that fast. But if you have a tertiary alkyl halide, this will go fast. Note this is the opposite we got with the SN2. With an SN2 reaction, primary alkyl halides do SN2 really well. Tertiary alkyl halides do not like to do SN2. With SN1, primary do not do SN1 reactions, and tertiary do SN1 reactions really fast. Why is that? The answer is carbocation stability. A tertiary carbocation is our most stable carbocation. It is more stable than secondary, much more stable than primary. Methyl carbocations are crazy unstable. So, a tertiary carbocation, that intermediate, is a more stable intermediate. Therefore, this reaction goes faster. We'll look at that in a second. And it is more stable, one, due to inductive effects. Alkyl groups are methyls, ethyls. They're slightly electron donating. They donate a little bit electron density to this carbon, making this not so positively charged. They weaken the charge, and the less positive this charge is, the less it's likely to be attacked by something negative, means the more stable that is. So the more R groups you have, they lessen this positive charge a little bit, makes it more stable. And there's another thing, hyperconjugation. We looked at it before, that this carbocation has this empty p, unhybridized p orbital. Methyl groups, alkyl groups can kind of stabilize that through this conjugation, a molecular orbital type look. All right. Now, when you deal with kinetics versus thermodynamics, recall that if you know the speeds, the forward rate constant and the reverse rate constant, recall that you can calculate the energy of the reaction. You can calculate the equilibrium constant, delta G, delta H, and whatnot. However, if you just know the energy, you cannot calculate the rate of the reaction. There are some very slow reactions that go all the way to the right, some very fast reactions go all the way to the right. So how is it that a more stable carbocation, if our carbocation is more stable, how does that lead to a fast reaction? How does stability here relate to speed? Because if you just know stability, in general, you don't know speed. Well, truthfully, it comes from our analysis of potential energy versus reaction progress diagrams and the Hammond postulate. What Hammond found out was that the transition state of a reaction closely resembles the structure of the species, the product or reactant, that it is closer to in energy. And we actually find this throughout chemistry. If you've got a energy, and you look at the energy of various states of molecules, it turns out the shape of the molecule, where the electrons are in the molecule, is much closer to where that molecule is in energy. What do we mean? Okay, let's look at this. Here we have an endothermic reaction. Here's our transition state. Does a transition state resemble the products, or does it resemble the reactants? Hammond says the energy of the transition state is closer to the energy of the products. Therefore, physically, the transition state looks much more like the product than it looks like the reactant. For an exothermic reaction, the transition state is much closer in energy to the reactants here. Therefore, in an exothermic reaction, the transition state looks a lot like the reactants do. It looks more like the reactants do than what the products are. All right. For an endothermic reaction, and this is what we're talking about when we make carbocations, the carbocations are less stable than our reactants. So to generate the carbocation, that step is endothermic. If we're looking at our whole reaction diagram, 2 pages ago, this first step to go get that carbocation intermediate right here is an endothermic reaction to make this carbocation intermediate. The carbocation intermediate is less stable than our reactants. So what that means is, since it's an endothermic reaction, if this was our carbocation intermediate, our transition state looks more like a carbocation than it does a tertiary alkyl halide. Our transition state looks a lot like a carbocation because it's closer to that in energy. That's what Hammond says. All right. Since our reaction is endothermic to make the carbocation, here's a carbocation intermediate, the transition state is closer to the carbocation intermediate than it is to the reactants. Therefore, the transition state looks like a carbocation. The transition state of this reaction looks a lot like a carbocation. Well, what stabilizes carbocations? More R groups. So what that means is, the long story short, since the transition state looks like a carbocation, anything that would stabilize a carbocation would also stabilize this transition state. More R groups stabilize the carbocation. Therefore, the more R groups you have, the more stable the transition state is, since it resembles a carbocation, means the lower that energy. A tertiary alkyl halide has when it undergoes an Sn1 reaction, has a transition state that looks a lot like a carbocation. So the 3 R groups on it stabilize that carbocation, which means lower its energy, which means it lowers the activation energy, and therefore you get a faster reaction. That's the Hammond postulate, and here is just some more words that say what I say. Yeah. Tertiary alkyl halides have lower energy transition states, have lower energy activation energy, and therefore go faster because many R groups stabilize carbocations. Therefore, they stabilize the transition state since it resembles the carbocation, since it is closer to the carbocation in energy. Okay. All right. So the next question then is, all right, we've looked at some situations. Question, when are we going to get an Sn1 reaction? When are we going to get the Sn2 reaction? How are we going to know by what mechanism the reaction is going to go? And that's what we will look at in our next video.